Thank you for the introduction. So today I'd like to talk about our recent work with Ben and Pratik, which is hopefully to appear soon. So let me start by the motivation of our work. So since last year, we have encountered significant progress on the understanding of the black hole physics, which is the entanglement island and the island formula for entanglement entropy. So this formula tells us about the entanglement entropy of subregion in the bath system, which probes the gravitational system using only effective field theory and the semi-classical gravity. More concretely, let's consider gravitational system, which is interacting with the bath system, which doesn't have a gravitational degrees of freedom. And then the entanglement entropy of a subregion A in the bath system can be computed by introducing the codimension 1 region I in the gravitational system, which is called the entanglement island. And the entanglement entropy is computed by the entanglement entropy of effective field theory for the subregion A cap I, the plus the area term of the boundary of the entanglement island. So this is the formula. So even though the entanglement entropy is a fine-grained quantity, without knowing about the non-particle gravity and stuff, we can compute the entanglement entropy. That is one surprising thing. And indeed, it's not just the entanglement entropy that can be drawn from this formula. So in particular, if you employ the idea of an entangled wedge, one can also say that the small excitation inside the entanglement island can be reconstructed in terms of the bath system. And nice thing about it is this formula can explain the page curve of black hole evaporation. So as a result, it resolves the forking information paradox. And it's also not just a conjecture, but can be proven using the gravitational path integral. So, but the resolution of the forking information paradox is not an end of the story, but there are many other interesting directions to research. And there are many long list of things to do with. But in my talk, I will focus on one research direction, that the entanglement structure of the forking radiation. So in this talk, we seek for the QI theoretic quantities or operation that probes the entanglement island or black hole or the forking radiation. So this is the summary of today's talk, as well as our research. So we we find the island formula for the bipartite correlation measure called reflected entropy. So this and the proposed formula can be applied to the strongly gravitating systems such as the evaporating black holes. So the form of this formula, it takes the similar to that of the generalized entropy. So we could call it the generalized reflected entropy. Yes, I just started recording. Okay, let me resume. So this is the summary of this today's talks, or summary of our research. So we will show that the reflected entropy formula, this satisfies all the required inequality, which will satisfy the reflected entropy. And we will also show that this new formula can be derived through the generalization of kind of a generalization of replica one-hole argument. So this formula is not just a conjecture. And interestingly, this new formula resolves some kind of information paradox for bipartite correlation, which I will explain later on. And finally, I will explain how the reflected island formula for reflected entropy can be used to probe the tripartite correlation in the evaporating black hole and radiation. Any questions so far? If not, let me explain what is the reflected entropy. So let's consider density matrix of subsystem AB. So by definition, you could think this density matrix lives in the tensor product of original Hilbert space and it is dual Hilbert space. So in particular, we consider the rho AB to the half, which is called the canonical purification. And we consider this state lives on this tensor product of Hilbert space and the dual Hilbert space. So why this is the canonical purification? So if you trace out HA star and HB star in this system of this state, then this state goes back to the original density matrix. So it's this state is a purification of the original density matrix. So of course, if you consider the entanglement entropy of this state of the subsystem AB, it just gives the entanglement entropy of AB system. But now you consider the different subregion. So when we consider the subsystem AA star, then this entanglement entropy gives new quantity, which we call the reflected entropy. So this reflected entropy has several nice properties. So when you assume that the original state AB is in a pure state, then it gives the usual entanglement entropy, SA or SB. So this is plausible since basically the unique quantity that measure entanglement in pure state is the entanglement entropy. So, but it is different quantity when you consider the mixed state. So the reflected entropy is one of the bipartite correlation measure, which is similar to quantum mutual information. And indeed, the reflected entropy has the following bound. So it's lower bounded by mutual information. And it's the upper bound in terms of entanglement entropy. So, but there's a difference between mutual information and reflected entropy. And the difference is these two quantities feel differently according to the tripartite entanglement of the state. Let us just take the example. Oh, sorry. For example, let's consider GHZ state. So GHZ state is written in terms of the state like this form. And it looks like, so it has a tripartite entanglement, but this entanglement is very fragile in a sense that if you trace out one of the system, it ends up in the following density matrix, which is a separable state. So this state has no entanglement. It's just a classical correlation. There's only the classical correlation. And indeed, in this case, the mutual information and the reflected entropy are the same, and there's no difference. But on the other hand, if you consider a different tripartite entangled state called a W state, this reflected entropy and the mutual information gives a different answers. And in this case, the entanglement is robust against qubit loss. So if you trace out one of the qubit, then the resulting state is indeed the entangled state. So we could say that by seeing the difference between reflected entropy and mutual information, we can see whether there's a robust entanglement, or we could call it the double type entanglement. Double type tripartite entanglement.
Masamichi?
Yes.
So here you had systems A, B, and C. And is your capital A and capital B, sorry, is the A and B that appear in the reflected entropy and the mutual information at the end, are those the same A and B that are the first two subsystems of this tripartite system?
Yes.
So you're only computing the reflected entropy and mutual information between A and B?
Yes. This is since if you compute like a reflected entropy A and BC, then since this state is pure state, it just goes back to the entanglement entropy.
I'm a little confused because I would have said that once I've traced out C, the state, as you noted, looks very different depending on whether you started with GHC or W.
That's true.
So you're saying, I mean, in one case it's entangled, in the other it's not. So wouldn't more primitive diagnostics have already distinguished these two states, rho AB?
Also, in both cases, GC state or W state, both of the state are kind of symmetric. It's equally entangled with each other. You could trace out A or B as well, and it gives the same result. Does that answering your question?
Oh yeah, I think it does. Thank you.
So using this difference, Chris and Pratik has argued that the polaric state must have this kind of robust tripartite entanglement by seeing the difference between the reflected entropy and mutual information. And I will use this difference to argue that there's a robust type of entanglement in the Hawking radiation in the later section. So actually this reflected entropy has a nice holographic dual called the entanglement cross-section. So let's consider the subregion. So now I'm going to the ADS-CFT setup, and I consider the boundary subregions A and B, and I consider the entanglement wedge of this subregion. So that the entanglement wedge is in the figure is in the pale blue region. And the entanglement wedge cross-section is a codimension 2 surface, which anchored from the boundary of this entanglement wedge. And also another condition is that the area of gamma is minimum. So it was originally the area of the entanglement cross-section is originally conjectured to be due to the entanglement purification, which is slightly different quantity than the reflected entropy. But last year, the Dutter and Faulkner has found that this is actually due to the reflected entropy. Okay, so now I move to our main proposal for the island formula for the reflected entropy. So let's again consider the gravitating system and the bus system, which has no gravitation inside, and couple these two systems by some interaction, and consider the two subregions in the bus system, which are written by A and B. And I want to consider the reflected entropy between these two subsystems in the presence of the entanglement island. So here I write island A cup B by as a island for the subregion AB, the A cup B. And I consider the kind of entanglement cross-section, gamma, which divides this island into two subregions, IRA and IRB. Then what this proposed formula says is the reflected entropy can be computed by the reflected entropy of effective field theory between two subsystems. And these new subsystems are A cup IRA and the B cup IRB. And we also add the area term, which is the area of this entanglement cross-section gamma. And then we extremize this sum of these two terms.
Sorry, is the notation here for the first term that it's the mutual information, or what is the colon doing?
So the first one, you mean the S effective R, right? So this SR is reflected entropy.
Oh, yeah.
Of the effective field theory. So it's mean so I'm now have the kind of two systems. One is original gravity, and the other is matter theory, which which I call effective matter, which live both in the bus system and the gravitational system.
Okay, and then my second question was, how do you know the islands are touching, or is that just a consequence of the optimization?
So you could say again?
Oh yeah, I guess it looks like you're defining the gamma as the place that splits each of the individual islands from the union of the islands.
Oh no, so IRA and IRB are not the island for the A and B.
Oh, okay, that's after the finding the cross section.
So okay, so in the end, actually the IRA and the island of A are different. In general, the island for A is included in the island IRA.
It might be useful to just briefly go back to that picture with the two, where A and B are sort of two intervals. Yeah, that.
Let's see.
Yeah, I get it. I think I get it now, where it's the IR parentheses A is the part of the union island that quote unquote belongs to A, but not the island that would have been found just by looking at region A.
So actually this picture is not very honest. So in principle, I have to consider the causal domain of dependence to compare these regions, but it's hard to draw, so I just omitted it. You could just think that it's a time independent setup. It's like this, but in general, it's so what I'm imagining is that this IRA is not in the same Cauchy slice as that of the island of A, in principle. But anyway, it's okay. Is there any other? Is there anything unclear about this formula? If not, I just resume. So this formula actually can be we could kind of expect it if you consider the double holographic picture. So double holographic picture, I mean, I have so originally I have the 1D quantum mechanics, which is attached at the boundary of 2D holographic CFD. So we consider the holographic dual of each systems. So for the quantum mechanical system is correspond to JT brane, and for the 2D CFT is correspond to the 3D semiclassical bulk. So, and then if you consider the entanglement wedge for the A and B, then the entanglement wedge cross section equal to the reflected entropy formula is just equal to the proposed formula for the reflected entropy, as you can see from the picture. So the entanglement cross section can end on either on the island or in some other boundary of an entanglement wedge cross section, which is pale blue subregion in the 3D bulk. But I emphasize that the proposed formula is not restricted to the holographic conformal matter, as in the original island formula. This is more general. And it is actually very easy to confirm that this proposed formula satisfies the plausible inequalities, which should satisfy the reflected entropy. So the positivity is obvious. And when AB is in a pure state, we should have the reflected entropy be equal to twice the entanglement entropy of A and B. And this can be derived by the same equality in the effective matter theory. So I mean this part. Can you see this my kind of arrow? And
Yes.
Okay, great. So this is now equal to the S entanglement entropy of effective field theory of A. So it's in the end, it's just the very definition of the island formula. So this equality follows. So how about this lower and upper bound? So I skipped the derivation here, but I just explained what I used here. So this inequalities follows from the very definition of the maximum. So we used in our proposal the maximum definition, and we also used the same inequality of that of effective matter theory. And finally, we also use the entanglement wedge nesting property, which will be explained by Misha next week. So we could say this basically follows from the QFC. Okay, so this is the inequality part. Any questions so far? Any unclear thing?
I didn't actually understand the argument for why, for the case where AB is pure.
Mm-hmm. Okay. So let's see. So here, so let's assume that the AB is pure. Then this SR effective is actually equal to the twice of S effective A, so the entanglement entropy of A. So what it means is this total sum is so okay. So in this picture, so A is subregion like this, and B is the outside, since the total system is the pure state. Then the area of this dividing surface is actually equal to the RT surface for subregion A. So in other words, the inside of this bracket is equal to the twice of the entanglement entropy for A using island formula. Is that clear?
I guess I don't understand two things. One is what islands have to do with it. In other words, already in the original proposal, surely there should have been an argument that you get the right answer if AB is pure. And then that would have to extend to the case where there are islands, just because that's just part of the RT prescription. Is that a fair statement?
So okay, what's
In your picture, it looks like A is clearly not AB is not pure.
right?
So that picture is probably no good for understanding this, right?
I have pictures here. So if I look, okay, let's think that A is this region and B is now goes to the infinite region. Then the entanglement cross section in this correspond to this curve, and the entanglement entropy for subregion A is coincide with this entanglement cross section.
Agree.
And if you consider more generic case, it's so in the case of AB a pure state. So in this picture, now the island for AB is the total JT brane. And if the entanglement, the dividing surface, which divide the JT brane into two regions, is just same endpoint of the RT surface corresponding to the subregion A. I'll come back to this in the last section. Okay. Let me go to the derivation of this formula in terms of gravitational Replica trick. So it is actually given by a kind of generalization of the Replica wormhole argument. The original Replica wormhole argument goes in the following way. So they consider the trace rho A to the n, which is given the Euclidean path integral. And this pale blue region is the gravitating system, and this red line is a subregion A in the bus, and this white region is a bus system. And you can compute the entanglement entropy using the Replica trick. And the argument was that when the entanglement between the bus system and the gravitating system is strong enough, this the saddle where the bus gravitating system is connected to each other will dominate. And when you take this replica in this n to the 1 limit, this replica 1/4 gives the exactly the island prescription. That's how the argument goes. And we can generalize this argument to reflect the entropy as I will explain now. So what is the replica trick for the reflect entropy? It goes in the following way. So we first consider the state corresponding to the rho AB to the power of m/2. So I generalize, I introduced a new parameter m and consider the Renyi entropy of subregion AA star of this new state. And in terms of path integral, it's you trace out HEP star subsystem from this state and to the power of n and take the trace again. So this defines some Euclidean path integral. Then in terms of this, the Euclidean path integral, the reflected entropy is given by the following limit of the partition function. I have note that we have to do the analytical continuation with even integer n, which is similar to what we do in the negativity computation. And the replica geometry for this partition function is given in the following manifold. So in particular, if you go through subregion A and B, it doesn't necessarily end up in the same replica sheet. So if you go through B in this replica sheet, then you go to this sheet. But on the other hand, if you go through the A, then it goes to this new sheet. So it's a kind of a complicated geometry. So in particular, if you circle around the boundaries of A and B, as you can see in the figure, you have to go through m different replica sheet. So for A, it's described by the arrows in the blue arrows, and for B, it's described by the red arrows. But on the other hand, if you circle around in a different way, like going from A to B and go back to B from B to A, then what happens is that in the most of the replica sheet, it just gives a trivial cycling. So it's just circle around once. But in some particular replica sheet with mu equal to 0 or m/2, here mu is this direction, and mu is this direction. So in this particular type of replica sheet, you have to circle around in the new direction, and one has to go through the n different replica sheet. So let's consider the replica geometry for the reflected entropy with gravitational system. And I assume that the bulk gravity can be treated semi-classically. So we don't need to consider, we don't consider the bulk to be quantum mechanical. So I treat it only with the consider the saddle point of the gravity with the partition function of matter theory. So as in the iron formula case, the geometry in the bulk could be connected or disconnected. And in the later case, what happens is that in each replica, bulk replica sheet has a conical deficit angles. And in the end, these conical deficit angles can be categorized into 3 cases. And one is the boundary of A prime, and second is the boundary B prime, which end up with the conical deficit angles with the following, which depends on them. And the third type is the intersection of A prime and B prime. And these intersections end up with a conical deficit angle depends on them. And in the end, I will end up with A prime is equal to IRA and B prime to be the IRB, and the summand of A prime B prime is the island of AB. So in the end, the reading effective action is decomposed into 3 terms. And since we take m and n to the 1 limit, each row can be extremized in the separately. And the extremization of first row gives this replica sheet goes back to the original background geometry. So it's just gives the equation of the motion for the original bulk geometry. And second row, it gives, as you can see, since this minimization is just that of the island formula, this gives the A prime B prime as the island for the A cup B. And third term is the minimization of this this quantity, which is the area of the intersection of A prime and B prime, plus the reflected entropy of A prime and B prime. So in the end, the 3 extremization gives A prime as the IRA and B prime as the IRB, and resulting in reflected entropy as the formula which we proposed. So this is the derivation in terms of gravitational reflectory or generalization of the replica one-form argument to this reflected entropy.
Masamichi?
Yes.
So I may be misremembering this, but there was some argument for the original proposal for reflected entropy the holographic proposal by Faulkner and
Yes,
by his collaborator, which I thought involved a sort of doubling of the
right.
of the boundary regions, and then just reducing to the usual RT prescription
Right.
for that doubled system. From that viewpoint, what is the what are the differences here, or what are the sort of the key new qualitative things that arise in your analysis because an island is present?
Okay, so here we followed more like the original Lukowitz-Mardasana type argument, and if you which was not.
So would it be fair to say that you're also kind of rederiving the RT prescription for that double system?
That's right. Yes, and if you follow the original Faulkner's argument in this case, so what should have to be done is that you have to prepare the double state for the coupled system, gravity plus the bath system, and that's so since so in that case we have to have a wave function for the gravity as well. So it's slightly more ambiguous to me, but it's a bit unclear. But we could also argue follow the original Faulkner's argument that preparing the double for the bus plus the island and apply the island formula to that double state and derive this the proposed formula. Okay, let's move to the final section. It's application. So I consider the most simplest example, the zero temperature eternally coupled 2D photographic CFT plus JT grav. The total action is usual JT gravity action plus the CFT action. And in this case, the double holographic picture is available. And I consider the subregion of A and B as the foreign form. And A now include the boundary of the bus system. So A is the 0 to the A, and B is A to the B. And I will consider the changing the boundary of A, and fixing the boundary, fixing the B. So in this case, both mutual information and the reflected entropy undergoes phase transition. So for the mutual information, so when the subregion A is small enough, this subregion B can have the island. But as you increase the size of A and shrinking the size of B, B has no longer have island. So the entanglement wedge of B undergoes phase transition and it's just the same as the usual entanglement wedge for the field theory. On the other hand, reflected entropy can also undergo like a phase transition. So when the size of A is small enough, the entanglement cross section can end on the JT brane. And as you increase the size of A, at some point, the entanglement cross section is shorter to end on this the pale blue line, which is the boundary of entanglement wedge for AB. And indeed, and actually this two phase transition doesn't coincide. And this is what happens in practice. So first phase, when A is small enough, the B has an island in the JT brane. And in this case, mutual information and the reflected entropy are equal to each other. So in this case, A is only entangled with B, not with the outside region C. And in this case, the entanglement is purely bipartite. But the situation is different in phase 2 and phase 3. So in the phase 2 and phase 3, we have the strict inequality, which means that the tripartite entanglement shared by this three subsystem can be said as a double type entanglement. So in particular, it has a robust type element. We can expect that that this tripartite entanglement is a robust against also the bounded subsystems. So by using the mutual information and the reflected entropy, we can gain some information about tripartite information in the radiation combined with the black hole. We can also say something about the information loss in the bipartite correlation. So actually the formula for the island formula for reflected entropy can be shown that it saves the unitarity by ending on the JT brane. So let's just assume the entanglement cross section doesn't end on the JT brane. So now the reflected entropy is now computed purely in terms of shift T, and it behaves as if there's no island. And this is the plot for the SR without island and mutual information. So in this region, as you can see, the mutual information is bigger than the reflected entropy. So this is since this inequality follows from strong stability, so therefore the unitarity of the theory. So this is a violation of the unitarity. So in the end, what the new formula for reflected entropy?
Masamichi?
Yes.
I didn't understand quite that last step. So I thought strong subadditivity was just a property of quantum mechanics.
Right.
Like it was a property of quantum states.
Yes. So
how's that related to unitarity?
So it also assumes the positivity of Hilbert space. So it doesn't. It also strong subadditivity assumes the Hilbert space is positive. And if this strong subadditivity is violated, it means that the Hilbert space has a negative norm state.
Is that the same type of breakdown of unitarity that we're worried about when Hawking says that information is lost?
Oh, that's a good question. So then I see. That's a good question, but let's see. It looks like so in the original type of for the unitarity problem in the entangled entropy case is that if you take if there's no island and take a to the size of A to be very small, even though the Hilbert space dimension of the gravity is finite, the entangled entropy diverges if we didn't consider the entanglement island. And that, yeah, I don't know how whether this issue can be caused from the negative norm state, to be honest.
I think it's more correct to call it like an amps-like paradox, right? Like where it's like internal inconsistency as opposed to like unitarity loss.
Yeah, I see. But
Yeah, I think this is right. I don't think we need to spend more time on that. I mean, I think it's clear that you know, since the island appears or doesn't appear, or you know, you end on it or don't end on it, it's really just a consequence of the quantum version of the RT prescription. If you don't do it right, you're going to get the wrong entropy, and then that wrong entropy is going to violate a lot of inequalities naively, since it's the wrong entropy.
Yeah, actually, this is the very end of my talk. Thank you for your attention.
Thank you. We need to solve this clapping problem on Zoom.
Yeah.
I think we have to unmute and then clap and then mute again.
Let's try it. 1, 2, 3.
Now it works. So any additional questions to Masamichi? So I think then, since we already asked a lot of questions during the meeting, we can send a message to Masamichi later, just in case. So thank you everybody for coming. And just to remind you that next week we have seminar again, and it's going to be Misha. He's going to talk to us. Okay. Thank you very much, Masamichi. So maybe some claps again.